In this video, we'll be solving another problem utilizing the techniques of Gauss's law. This problem is a little more subtle than typical Gauss's law applications, but as usual, the mathematics will not be hard, just a conceptualization. So let's take a look at the problem statement. In this problem, we're asked to find the electric field at a particular point on the x-axis. What we have are two spherically symmetric charge distributions, so we can imagine that because there is a lot of symmetry in the problem, hopefully we can exploit that along with Gauss's law to help us find the electric field. Let's just recall what Gauss's law states. And Gauss's law states that the electric flux through any closed surface, and that closed surface is your choice, whatever that closed surface is, the electric flux through it, in other words, the integral of the electric field over the area of the surface, only depends on the enclosed charge divided by a constant. Okay, so in this case, what we're going to do, as typical with Gauss's law problems, when we're asked to find the electric field, we are just going to have to find our own Gaussian surface. In other words, define this surface for ourselves in such a way that if it exploits a symmetry, we can solve this very easily for the electric field. So if I just redraw this picture, a quick sketch of that. Now what we're asked to find is the electric field somewhere about over here. The radius of this circle is 3 centimeters. We're asked to find it at x equals 2 centimeters, which is inside of this first ball of charge. So what you also want to do is when you're asked to find the point at a particular point, find the electric field at a particular point, you want to draw a Gaussian surface that intersects that, and that way you can find the field along that surface. So we'll draw a Gaussian surface that respects the symmetry of that sphere, which looks like another ball inside of that one, with a radius of 2 centimeters. Right? Now, if I write down Gauss's law for that particular sphere, which has a radius, let me just call the radius r, or the radius is actually 2 centimeters, so let me just call that r is 2 centimeters. And if I write down Gauss's law for that, it states that the electric flux over that surface has to equal the enclosed charge divided by epsilon naught. Well, how much charge is inside that Gaussian surface? None, because all the charge is outside of these two balls. So we have 0 enclosed charge. Which indicates to us that, well, does that mean that the electric field equals 0? Actually, that's incorrect. But I want you guys to reason out what it is that, despite the fact that the enclosed charge is 0, prevents us from concluding that the electric field is 0. Take a minute, reason that out, and we'll come back and take a look. Now, the reason we can't reach this conclusion that the electric field equals 0 anywhere along the surface is that this Gaussian surface is not a good one for this problem. And the reason is the following. We've drawn a surface that respects the symmetry of this sphere, but doesn't respect the symmetry of that sphere. In other words, if we had just this sphere by itself, but not that one, we would certainly not draw a Gaussian surface over there. We'd have to draw it inside of here. This sphere is symmetric about that point, but not symmetric about the origin. So because this Gaussian surface does not respect that whole symmetry of the entire situation, then what happens is you cannot bring this guy outside of the integral. You can only bring it out when it's uniform everywhere on that sphere, but if you don't respect the symmetry, you can't bring it out of the integral. So because you can't do that, you can't say that E equals 0 divided by A. All you can say is that the full integral over the surface ends up being 0. And the reason that happens is because you have all different fields all along this surface, but they end up canceling to 0 when you integrate it over the surface. That doesn't mean that at any certain point the field is 0. So the problem here is that we haven't drawn a Gaussian surface that respects the symmetry of the full problem. And this particular problem has no symmetry because there's two different parts that are radially symmetric about different origins. So how to proceed? The way to do this problem is to break it up into parts. Use the superposition principle. In other words, let's find the electric field due to just this ball of charge, and then we're going to find the electric field due to just this ball of charge, and we can add them up. So we'll do those one by one. So if we do shell 1, and what we have is this shell, and what we're looking for is the electric field at this point right here at x equals 2 centimeters. And so we can use a Gaussian surface for this one that looks like this. Just the one we drew earlier. Now this one is going to be useful because now if we use Gauss's law, we have that this equals the enclosed charge, which is 0, of course. Again, we're just considering this one shell by itself, so we can ignore this shell for now. There's no charge inside this Gaussian surface, so the flux is going to equal 0. Now, the key here is, can we bring E outside the integral? In this case, we can because this respects the symmetry of the entire full problem here. And so everywhere along the surface, E will be the same, which means we can take it out of the integral. And so we get E equals 0 divided by the area, which is just 0. And I'll call that E1 because that's the electric field due to the first shell. Now for the second shell, I want you all to do that on your own. To do a similar thing, and in this case, we're just going to draw the second shell, but not the first one, which is centered somewhere over here. And what we're looking for is the electric field, again, at x equals 2 centimeters. So draw the appropriate Gaussian surface, set up the Gauss's law flux integral, and try to solve for the electric field due to this ball of charge alone. Take a minute, and we'll come back and take a look. So as always with Gauss's law problems, first get an intuition of which direction the electric field points using the symmetry. We have something that's symmetric about that point, so we can imagine that because it's positively charged, all the electric fields around it will point radially out from the center of the charge distribution, so it'll kind of go like that. We're going to draw a Gaussian surface that respects that symmetry. In other words, we're going to draw it kind of like this. Okay, so notice that this Gaussian surface is distinct from that one. This is why we couldn't do it all in one shot, because you had to have two different Gaussian surfaces. Now, this guy has a radius of this distance for the Gaussian surface. So now applying Gauss's law, we have that the flux equals the enclosed charge divided by epsilon naught. The flux is, now because we have the surface normal and the electric field are perpendicular everywhere, E is constant along this due to the symmetry. We can take it out. So we just have E times the area. And the area in this case is the area of the Gaussian surface, which is 4 pi little r squared. Okay. Again, this area is the area of your surface along which you're integrating the Gaussian surface. And then the enclosed charge, well, we don't have an enclosed charge value. We do have a charge density. So we can convert this from a total charge to a charge per area times area. The charge per area is this value, sigma 2. And the area is the area along which the charge is distributed. So this is going to be the area of this of the charged ball, not the Gaussian surface. And the area of that is going to be 4 pi times r2 squared. And then finally, we're dividing by epsilon naught, which tells us that, and I'll call this E2, this is the field from the second charged ball. Finally, this tells us that the electric field is given by, let's see, so sigma 2 times r2 squared divided by r squared epsilon naught. All the 4 pi's and stuff cancel. All right, so we have values for all of these guys. We do need a value for little r, which if we just look at the geometry of the problem, this distance is 10 centimeters. So between the centers is 10 centimeters. And then we're looking at 2 centimeters away, so the radius here is 8 centimeters. So plugging this in with little r is 8 centimeters, r2 is 2 centimeters, and then the value given for sigma 2, we get an electric field value of 2.8 times 10 to the 4 newtons per coulomb. Okay? So finally adding up these two electric fields, well here it points in the negative x direction because it points radially outward from the charge distribution. So because E2 points in the negative x direction and E1 is 0, the net field at x equals 2 centimeters, which is what we're trying to find, is just equal to, in unit vector notation, 2.8 times 10 to the 4 in the I direction, negative I direction, because it's pointing in the negative x direction, and the units is newtons per coulomb. Okay, so this problem, again, was not mathematically tricky, but it was a little subtle and did involve a solid understanding of Gauss's law. Let's take a look at the summary. In this problem, we were asked to find the electric field due to two spherical charged shells. We recognized first that Gauss's law was not useful in the presence of both of these shells, so instead we determined the field from each shell individually, exploiting the symmetry to properly apply Gauss's law. And then finally, using the superposition principle, we added these individual fields to get the net field at the point indicated. I hope this is a useful example problem that highlighted the care that you have to take when you apply Gauss's law properly. If you have any comments or questions, please leave them on the link attached to the video, and we'll see you next time.